So we have an awesome keynote from Roy Frostig, who is one of the co-creators of JAX and research scientist at Google DeepMind.
Thank you. I'm Roy. Thanks for the intro. So I'm a researcher at DeepMind. I work on JAX. I also, we do ML and systems research as well to help build our Gemini models, and all these things inform one another. And I just want to say, whenever I talk about JAX, I'm always covering the work of many people, people on the JAX team, other colleagues at Google and Google DeepMind, across Alphabet, JAX, XLA, TPU, across the world, collaborators from places like NVIDIA. So one thing I'm looking forward to most is having a lot of these folks here today, and when the talks are done and so on, meeting each other and talking to each other. I think that's really the goal here. So to get us started, I'm going to talk about JAX, surprisingly, and then about some projects that are built around it. As you may know, like JAX is sort of the bedrock of a lot of ML research. It powers a lot of ML research and large models at Google and many places across the industry. How do we do that, right? Is the question I kind of want to ask. Between this talk and Matt's talk later, we'll underscore how the thing we're doing is kind of bringing more and more programming models to your hands, right? And all these different programming models are all in one library. And for this reason, I've titled this talk "Programming Models for Programming Models." And before I get right into that, I want to start with kind of where we are as a field, a few words about that. And that is that arguably we're in an era of big matrix multiplication. We're still in that era. Maybe not the first one in history. Some might say we've been in it for decades, millennia. And sometimes people ask what I do for a living, and it feels like multiplying matrices is roughly the answer. Of course, I hardly ever multiply them myself. So we make hardware to multiply matrices. We make software to multiply matrices. Recently, that software is making software to multiply matrices. And we're all just getting all these numbers multiplied and added. And how's that, what is that driven by, especially recently? I'd say there's, in this period where there's been two concurrent, very productive trends that were unlocked several years ago and are still going. And the first is that we keep steadily producing more and more compute resources, right, from silicon or from sand. And we keep also steadily converting at the same time those compute resources into good stuff, like language model capabilities. So we just keep doing this. We keep finding ways to turn sand into flops and flops into intelligence and other things, right? Scientific results, things like that. So in the first trend, what do I mean? The flops just keep coming. The rate, what I mean by that is that the rate of floating point operations per second, sometimes int operations per second too, is very roughly, it's been common to see the peak flops rate, for example, of our hardware, of our GPUs and TPUs, roughly double or more with generations of this hardware. I say roughly because we also switch floating point precisions and change to integer precision sometimes. Or we change the overall system to connect a different number of chips. So, there's a bit of, putting things under the rug there. But overall, the flops are growing. The amount of memory we have is growing. Capacity and bandwidth of that memory is growing. And that's great. I thank the hardware engineers for that. And then in the second trend, we're turning these flops into AI results, engineering, scientific results. You have researchers, scientists, and engineers, many of whom are in this room, just basically, I don't know how we do it, but we keep finding ways in machine learning, for example, to convert these flops into results. Right, so we're seeing this empirically, very steadily, even predictable amounts of progress on language model capabilities, for example. We look at benchmark scores there, and they, whenever we put more flops into them, more operations go in, the benchmark accuracies go up. Over time. You don't have to take my word for it. This is like a point made in papers and reports on scaling trends. You might also be feeling this trend yourself, maybe in your work. Maybe you're coding with AI or writing with it and you feel it there, or maybe you see it in the scientific work you're doing. But that's all to say that, like, quantitatively and empirically, the two trends are both happening. And while the hardware engineers are holding up the first trend, their end of the stick, right? They're printing chips from fabs and putting them into racks and making TPUs and GPUs go burr, as they say. We're getting more value from it every year But our job as researchers, engineers, and scientists is to hold up our end of the stick, right? To keep that trend going and convert these whatever exa, zeta, yada flops into good stuff. So in other words, that arrow there is something that we all need to keep very strong. And I think what we'll see in part today is how the tools and libraries and ideas that we're all bringing to this workshop are shaped by that scaling trend and designed to make the most of it. I'll start by highlighting what JAX is doing to help kind of keep this trend alive. Again, the theme will be programming models. So how do we do this? How do we turn compute into intelligence? Well, I think, roughly we do 2 steps. This kind of work falls in 2 steps. We do some research, and then it's followed by some engineering. Easy. Let's go into each one in detail. The research one. In the research case, what I mean by research is something like algorithmic exploration, modeling. If we focus on, again, language models, which is where many of us are, have our heads right now, or even large-scale ML more broadly, then what I mean by research is things like new model architectures. Maybe you're working on a variant of attention. You're maybe working on model scaling, studying the scaling laws of models as they grow. Maybe you're doing algorithmic exploration, like how to use new optimizers in training, or how to make use of reasoning. And this type of research happens typically at, importantly, many scales of compute. Like you might be doing this at small scale on your laptop, probably a bit more than that. These days, you're really operating at like medium to large scale, right? Like you might take some open model and work with it. You might be at a frontier lab and working in really big models. But you're doing exploration here at medium to large scales. Still requires quite a bit of compute, and the most important thing to you is fast iteration, right? You really want to minimize that time to results. So you want to minimize the time it takes to find something new, and that includes development time. You don't want to be spending all your time, writing low-level code to make it possible. Another way to say this is that the programming need you have is one of flexibility. I say flexibility, I mean flexibility in the face of like your code changing. You might have a new idea and you want to be supportive of that code change, or flexibility in the sense of your topology, your hardware is changing underneath you, right? You might find that you have a bunch of, a new cluster to work with. You want to move to that, take advantage of it. So you want to be flexible in the face of those changes. And the way we approach this in JAX, in terms of how we've taken guesses at the APIs that help here, is we say, why don't you just write math, right? Why don't you just write NumPy and describe mathematically the program you're trying to write, and then take advantage of compilers like XLA to sort of let it take over the rest, right? Have it drive the way your math is mapped onto these big machines, and take it from there. Then comes the engineering side of things. When you have had all your brilliant discoveries, you've decided what to do, it's time to train a model at the largest scales, or just double down on the ideas you've already developed and bring them to to product or something. Then at this point, you start to care a lot about squeezing the most out of your hardware, right? And you're ready to commit to it. So why is this hard? Why can't we just use the compiler to do the same thing? Well, a lot of the time it works, right? It isn't always hard. It doesn't always have to be hard. But at the highest points of scale, you run into issues. For example, it's one thing to stand up here and say, oh, these flops, they keep coming. We just crunch numbers. Life is good. But in reality, you have this really nice hardware sitting in the data center, and it's not always crunching numbers. It's not always multiplying matrices. You can spend a lot of time waiting on data movement, waiting on your arrays to get into the right place, waiting on that right-hand side and left-hand side of the matrix to get into where they need to be before we can do the matrix multiply. Moving between local memory or across the network. So we don't want to leave these flops stranded, waiting on data movement. We want to overlap communication and compute. We want to do all these things. The compiler typically does a lot of this for us pretty well, but there comes moments where we just really want to take the wheel from the compiler and do it ourselves. And so JAX's approach here is to kind of selectively let you drop into lower level programming models for control of the hardware. There's a very natural trade-off between what I described as research and what I described as engineering. So when you're doing the sort of research work, when you're being more exploratory, it might make sense to hang out on the left side of this curve. What I've drawn here, though, is sort of cartoon plot of a trade-off, where on the left-hand side, you want more flexibility, and you don't need to control the machine as directly. And on the right-hand side, you kind of walk down the features we've given you here and take more and more direct machine control. And then as you do so, naturally, you are a little bit less flexible. You're committed to the hardware more and more, and you've made specialized decisions. So Matt will go into some of these in detail in his talk. I'll just kind of gesture at them very briefly. If these are a few features I've chosen to highlight, the only features in JAX, but there's some pretty, they include some pretty exciting recent ones. If you're familiar with JAX's APIs, if you're doing research, you're probably hanging out a lot in the top left. You're writing NumPy, you're compiling with JIT, sending it to the XLA compiler, and it takes care of the rest. You might then choose to take a little bit more control and hint at the compiler, give it sharding constraints, and say, my data lives in this configuration at this point in the program. We have a new feature, fairly fresh, that we call explicit sharding, where for each expression in your code, the sharding is known. You can inspect it. It can be reflected on. And if there's any ambiguity as to what the sharding of an intermediate value is in your program, then, or if there's a mismatch sharding, in there that might cause communication, we raise an error. We require explicit annotation for it. This is a mode you drop into. So you're not there by default, but you can opt into this on a mesh access. And of course, it works under JIT. And the overall gist of what I'm showing you is that we're giving you more control. By default, the compiler would pick the shardings. In this case, instead of handing it to the XLA compiler to figure out, you can take over. Obviously, when you do that, your code becomes a bit less flexible. Your decisions to shard one way or the other might be brilliant on your current generation of TPU or GPU. They might be not so brilliant on the next one that comes out, or you get a bigger pod or a bigger configuration. So in that case, you can drop back out, go into math, and get back into it. Down from there, we take it a step further. You can drop into JAX's shard map, which lets you control the collectives that transfer data between devices. And down from there, you can take even more control of the device you're programming on and write kernels in a mini language we call Palace. This is a way to control very specific data movement, like things like moving from HBM to local memory to registers, and when certain ops get run, and so on. So as you do this, the theme is that at a high level, when you're on the left side of this curve, you're writing math, and as you kind of go to the right, you are more directly touching physics. You're moving bits around. And also on the left, XLA is our main engineer, and on the right, you're more of the engineer in control of parts of the code. Stepping back up from all this, it's common to say that JAX is very functionally oriented. It's typical that when we say JAX is all about rewriting JAX, you have to get into functional programming. That's true, but you see that these different programming models are all mixed in as you drop in and out of them. Right? We have the functional ones, kind of writing functional code when you're doing NumPy and JIT. When you write shard map, you're in more of an SPMD mode. It's still functional, but you're controlling collectives. And Palace is imperative. We have a new experiment that Matt will also talk about, where we're introducing imperative style code even at the highest levels of the function of the spectrum here. And we call that mutable arrays. So overall, I'd say that we see JAX's job, the JAX team, the JAX development project. Our job is to kind of find new dots on this frontier, right? We're trying to make new features, discover the basic primitives of machine learning and numerical computing that trade off control and flexibility in this way. And we hope that we're discovering things that are at the Pareto frontier, and we want to keep pushing that out. And as we do that, we want to make sure that it's all composable. So you can call shard map from within a JIT, step back out. You can take grad of that, take vmap of that. The usual thing where you don't have to leave the program or write your kernels in one place and call into them from another system, and so on. Similarly, you can call Palace. So this has been our MO for the last couple of years, is uncovering all these basic pieces that are hopefully at the frontier. And we focus on that and finding these fundamental pieces and giving them to you. And I want to just say a few words about what people are building on top. So if JAX creates the fundamental basic building blocks and discovers them and hands them to you, it can be a little bit bare bones sometimes. It's very natural for people to build frameworks and toolkits and whatever and libraries on top of it. And I think that's actually what brings a lot of people to this room to begin with. So there's been a lot of activity over the years in what you might call the JAX ecosystem. There are many projects. They end in X a lot of the time. Don't always do. And I think that this is actually some of the best ways that we get sort of effective contributions to JAX, right? Like JAX open source project, you can contribute to it directly, but you can also contribute by open sourcing your own library on top into and kind of bringing it into the discussion. Highlighting some trends in the ecosystem that we've seen over the years. There's been, obviously, when we started JAX, there was this big boom of neural network frameworks. People were kind of trying out different designs in the space. I'm going to sort of wager a guess that I'm seeing a bit of convergence in that space now. Things are either becoming like more the Flax NNX model or the Equinox model, or kind of derivatives and variants thereof. But overall, still going strong. People like these. There's the utilities side of the ecosystem, things like JAX typing and checks. There's a question of why those things sometimes aren't in JAX core. I think it's another area where these tools are providing opinionated additions to JAX, and it's nice to see them kind of bloom. We have a long history of being used in simulations and reinforcement learning, where there's a lot of embarrassing parallelism to take advantage of. Right, so if you're doing molecular dynamics simulations, or there was this library called BRAX that did physics simulations for a while, you can expect to benefit from a lot of parallelism, and JAX's VMAP and parallelism APIs help there a lot. We have scientific computing, which is kind of the OG matrix multiplier, right? Like the big field that was around and multiplying matrices before we were all born, still going strong and making a lot of use of these things. And we have, of course, LLM code bases, which we've seen emerge recently. And this is maybe the last comment I want to make here in LLM land. We have, LLM code bases do things like training of language models, serving of language models, inference, and we see a lot of them. There's one from Stanford called Levanter. There's one from Berkeley. There's one from Apple called Axlearn, and one from Cloud called MaxText. And you can even use pure JAX. There's some examples in the JAX. It's called JAX LLM examples in the JAX GitHub org, where we've shown how to do like one file inference of certain models. So why are there so many of these again? Kind of like the neural networks frameworks back in the day, maybe. I think this is a bit unlike that, actually. There's maybe some exploration of taste, but fundamentally, the guess I have here is that this is because labs have fundamentally different needs, right? So, for example, the folks at Stanford CRFM really care about legibility and reproducibility, and so they've taken JAX's pieces and decided to adapt them in a particular way, right, to suit those needs. By contrast, maybe MaxText, which is developed by folks at Google Cloud, in many ways, what they want to do with this code is demonstrate the top line of Google TPUs or Cloud TPUs. So the question I want to leave everyone with as we go into talks and then hanging out after that is, well, we've built these pieces. They work reasonably well for uses at Google. They work reasonably well for a few labs here that we're highlighting. And I want to know if they're working for you. So thank you.